Okay, then let's go ahead and get started today. Last class period, I talked about a type of antenna that was very commonly used in UHF and microwave engineering called the Yagi Buddha array, just a Yagi for short. It was a beautiful little antenna, very simple to design, at least deceptively simple, but it was still an example of an antenna that you need to apply numerical techniques to really get the right answer. We could make assumptions about the standing waves on those little dipole elements that are used to make up a Yagi Buddha array, but unfortunately, getting the phasing properly between elements is very difficult. In fact, that design is very sensitive, and the technique that I outlined today will tell you how to do it. I'm just going to outline the basic kind of rough estimate of how you would solve this problem numerically. And then I'll point you for your next homework assignment towards a free version of this numerical solver that you can download on your own computer and set to work. It's called NEC. It was one of the very first numerical electromagnetic codes ever written. In fact, NEC stands for Numerical Electromagnetic Code. That's how old this thing is. It was originally written in Fortran, probably in the early 70s. And it's a beautiful way to solve for radiation problems for pieces of metal and wires. And it's sort of the granddaddy of them all. And we'll look under the hood and explain how it works today. I'm not expecting you to reinvent the wheel and code up your own numerical electromagnetics code. If you want to do that in MATLAB or whatever programming language you like to do, knock yourself out. We're going to learn how it works. Why do you have to take pieces of metal and break them up into segments? Why does the input look the way it does? And one of the nice things about a well-trained engineer is that you often have the ability to check the computer. Computers are dumb. They only do what we tell them, right? And so if you don't have that intuition, it's very easy, very, very easy when you're operating numerical software packages for antennas and other radiation problems to get nonsense out. And at a lesser institution where they do not teach antenna engineering, they do not give the intuitive background of how antennas work, the engineer will just uncritically pass that along. And then, several months away, several design iterations down the line, and a few $100 million later, they will wonder why their product line is not working properly. I don't want that to happen to anybody in this class. So we're going to learn how it works today so that you can kind of make sense of what the computer is doing and what it puts out. And then from there, we'll go on to a little bit of array theory. Having finished up the most simple kinds of wire antennas, then we'll put it all together in a very elegant design for an antenna called a helical antenna, which can be modeled as actually an array of circular ring antennas, which is why we do it in this order. And then from there, we move on to some interesting antennas involving open waveguides, horns, flaring out waveguides. What does that do? Reflector-based antennas like parabolic reflectors and the like. And then we'll be almost done with the class. I mean, that's going to take us to like November to get all that stuff done. Now we'll be approaching test 2 soon enough. We'll have to test on all that stuff. And then I may throw in a couple special topics to help your project. Okay, any questions before we get into the meat of the material? Before we do the math and start mathing all over the board, I brought in an example of kind of an unorthodox Yagi antenna. It's based on the exact same principle, except instead of using a half-wave dipole as the driving element, it uses a V dipole. We talked about the V dipole in this class, Emmy. It's just a dipole, but you bend it over a little bit, and it makes a little traveling wave. It actually pushes the directivity of a dipole in one direction instead of keeping it omnidirectional. So it's got a cross between a transmission line, which of course would just reflect the wave back from the end, and a half-wave dipole, which of course makes a standing wave that radiates nicely in space. You kind of make, it's a halfway case. You launch a wave that way. It has a slightly different impedance than a half-wave dipole, but a little bit of front-to-back ratio. So you already have a little bit of directivity. And then if you add a slightly smaller V in front of it, it excites parasitic currents. They're phased in such a way that it acts as a director, adding directivity in this direction, taking it from the backside. And likewise, you can also, it's not on the same plane on this circuit board, but then there's a similar V element on the backside that's a little bit bigger, and that causes a reflection in that direction as well, serving as a reflector. This is kind of an engineer buddy of mine with Albert Liu made this antenna. It's a beautiful design, 10 dBi of gain, which for this antenna size is pretty good. You might only be able to do maybe 7 dBi of gain for a regular Yagi antenna element with 3 elements on it, a driver, a single reflector, and a single director. This you get a few more dB because he bends it in a particular direction. Again, an antenna that would only work and be designed if you had a numerical package on there, because this becomes more complicated than the regular run-of-the-mill even Yagi antenna. If you want to take a look at this, it's built on FR4. It resonates at 5.8 gigahertz, and it's connectorized to an SMA connector, to a standard RF cable in your microwave lab to it. Those of you who are in the lab, measure this sucker. Any questions about this show and tell? Oh, let me hold it up here for the people at home to see. Here's the Yagi Buddha array. That's a V dipole. And trace on the back, SMA connector. 10 dBi gain in that direction. Pretty good front to back ratio too. Yes.
Is the trace on the back?
Yeah, it's a topology problem, right? How do you feed the driver in the center when you've got 2 shorting bars on the same plane? So if you see, they actually put a quarter wavelength balun on the center feed where it feeds back into here. But that will look like an open circuit here. It will suppress any outer unbalanced currents, and it will still allow this element to be driven as a regular V dipole element. But yeah, it's a topology issue. You see what he's talking about. We got 2 up here, and then the reflector, which the director and the reflector aren't connected to anything. They're just true parasitic elements. But the director's on the back so that the trace can go. The reflector is on the back because the trace has to go and feed this director here. We'll look at that later after class when you're done with lecture. Okay. Now, remember we did that standing wave analysis, which we started with the very first week of class. What do standing waves of current look like on a piece of wire and a transmission line, and a transmission line that you bend? What we were actually solving when we did that is something called Pocklington's integral equation. And the way this works, Pocklington's integral equation says that the E field, E direction, that's impressed on a section of wire immediately outside that wire, that E field should be equal to 1 over J pi F epsilon naught. Integral from minus L over 2 to plus L over 2. The current evaluated at a section E times this a Green's functiony looking thing Here's my point of observation. Here's my variable of integration, like we always do in this class. Partial derivative of the point of observation with respect to z plus k squared psi z prime dz prime, where psi is just a helper function, exp to the minus jkr 4 pi over. This with a graduate class, we would spend a couple days deriving this result. But we're not going to do that here. And when we talk about z and z prime, what we're really doing here is, let's say we have a z-directed wire. And there's currents on here. Currents as a function of z prime, a point of observation along that wire. Or a point, a variable of integration. The point of observation is where I'm observing the field. The eye. So what this is really saying is that my current on the wire is related to the field excitation. They're related to one another, and it's and here is the fundamental problem with studying antennas. They're related by an integral equation. When you use the term integral equation in antenna mathematics in general, you're not saying, oh, this is an equation that involves an integral. You guys know how to solve those equations. You've been doing it for years. You can integrate stuff, right? So what makes this an integral equation and particularly hard is that the thing that you're usually trying to solve for is underneath the integral. This is your boundary condition. This is your integral. The I means an impressed field, a field that you have put onto the element. So for example, if this was a half-wave dipole, our I as a function of z prime is unknown. However, our excitation would be a voltage right in the middle of the thing, right? That's where we usually excite half-wave dipoles or dipoles of any nature. So we'd have a voltage from a transmission line, bringing a voltage up here and exciting E sub z, not putting any other field, any other impressed field along that line. What would happen? What is the I that results from that? And we can see kind of the your standard propagation terms. Okay, it makes sense that the field here is going to be influenced by the current here. And there's an exp to the minus jkr case, the free space wave number. There's, of course, a frequency dependence here. The influence is going to fall off 1 over r, just like any other field expression. So how would you go about solving this? So to solve an integral equation, we have to discretize the system. And the way that we do that is breaking our wire up into segments. So we go and take a look at this wire. I'll blow it up here a little bit. I'm going to break this up into n segments. What does I do? N equals 7, it looks like. We'll make 7 uniform segments. And the way that I will write this then is that I function of prime is going to be approximately equal to sum n equals 1 to capital N, 7 in this silly little diagram. I'll have I sub n, that'll be my amplitude sample, which of course can be complex. I should put that in there. And then this kind of shape function, f sub n, which is basically an artifact of the discretization. So if I had a graphic where z was in the horizontal axis and my f of n prime, if I graph those different functions, f of 1 would be this function. If I chose a uniform discretization, this would be some sort of delta z, which would be approximately equal to the length divided by the number of segments that I discretized. L. And then this is my f sub 1. And then using multimedia colors, this would be f sub 2. This would be f sub 3, and so on and so on. So we are using these discretized chunks of wire, and these helper functions basically turn on and off the various samples of I sub n. So there's going to be a discretization error in our analysis because we've introduced a function with finite samples, right? What we're really saying is that the current that I'm going to model here is probably going to have some sort of stair-step shape when I add all this up, right? It's going to be something like that. And you know what? That's okay. That's part of your discretization error. And in fact, what we'll see, and what you'll see when you start playing around with the code, is that up until a point, this thing can be very sensitive to the number of samples in your simulation. If you have a half-wave dipole, you got a half-wave length of a wire to break up into little hunks. And if you only break it up into 3 hunks or 5 hunks, you're not going to get the right answer. But if you use like 9, 10, 11, you'll get a really nice answer. If you use 20, you'll get a great answer that won't differ that much from your 10 sample error. And if you put like 100, as we're going to see in a second, to solve this technique, it becomes kind of like one of these order n squared or maybe even n cubed pivoting problems for matrix inversion. It gets to be a very difficult problem numerically, which is why electromagnetic solvers are very difficult to work with sometimes. A appreciable electromagnetic sized problem. So what we'll do now, let's go ahead and take this and plug it into here, our sampled value here. So what this then looks like, go ahead and get some space to work with. Sure. Glad we finally got one of these. Let's go ahead and plug that value. We now say that this is going to be equal to 1 over j IF epsilon naught. I'm going to put that summation in here, but I remember that summation and integration are both linear operators, so I can interchange them. So the key simplification I'm going to make is I'm going to take my I sub n summation outside the integral, where I have just I sub n constant terms. Again, this is, of course, just a constant. And what I'm left with is the integral from minus L over 2 to L over 2 of my Fn shape function, and then this messy thing up here. Second partial derivative with respect to z of my psi helper variable function plus k squared psi z prime z prime. Okay. In fact, let me do this. It's going to be even simpler. You'll see I'll be able to do. I'm going to interchange these. Wow. That gives me the result a lot more intuitive and will make more sense. Second, because the new units of this thing on the right basically ohms per meter. I'm going to call that delta Z Mn. So it's going to be the sample for the nth current. That's complex. Nth current sample. And what's more, I'm going to basically have to integrate this, or this is going to give me the nth sample of my field. Does that make sense? We have a long wire. We're breaking it up into samples. We sampled the current, one here. We're going to have to sample the field, too, making it correspond to these delta Z segments at the field moments. In fact, what we would like to write this as minus EZ. I'm going to write this as the mth voltage sample, the voltage drop across that delta Z element in the mth sample space. And of course, I'm going to have to divide by delta Z to get this also into a field. Remember, field is negative the gradient of the voltage. So if I divide the voltage by delta Z, I get something that's proportional to the field. And I have to put a minus sign in front of it as well, because E field always points from positive to negative voltage. Yeah, very high. So they're both the samples along that discretized wire. N is being used to calculate the contributions of N. So this sample, this sample, this sample. M is being used to track the sample for E field, which is the same location but different, right? So what I'm saying is that there's a system of equations when I sample the problem that says E sub M, let's say E sub 1, is related via this complicated expression to the first, second, third, fourth, fifth, sixth, and seventh current distribution. And I'm picking up those contributions when I step through from 1 to 7 in this expression. Then I move to the second sample, the second location, and I have to recalculate all this again. I'm still stepping through all 7 samples of current, but the weighting factors are different. This integral is going to be evaluating differently because now it doesn't matter what happens, right? Whether I change my point of observation, D, or my variable of integration, the collection of integrands changes, no matter what contribution I'm trying to compute. So this is really, this integrand or this integral expression will be n, there will be n squared different evaluations of it, right? Because I have 7 possible locations for my E field to calculate or my voltage. And all 7 currents contribute to that. And none of them in quite the same way, unless we have a geometrical accident of symmetry. So that's why, now you see why this integral equation business is so difficult. It's hard to solve for something under the integrand. Because if this was a problem that required 500 sample discretizations of a fairly large electromagnetic problem, even if it was a simple wire antenna, that would mean I would now have 500 squared computations to make here. Then I got to invert the sucker. The nice thing about all this, though, is that it puts everything, the way that we've set the problem up, it actually puts everything into a very elegant and familiar form. Just look what I have here. I have, let's make this complex, voltage samples, amplitude and phase, divided by delta Z. That is equal to current, a bunch of samples of current, times d sub mn, delta Z. So if I wanted to, I could write this as, I got 2 delta Z's, I can make that cancel. d sub m is equal to the sum of Zmn times I sub n, which looks a lot like what? Looks like Ohm's law, right? In fact, if we're comfortable with matrices, it might even be better to write it like this. My vector m by 1 vector could be square, so we can use n. My n by 1 vector of complex voltages is equal to my complex Z matrix, which is n by n, multiplied by the currents, which again are n by 1, a vector of complex currents. And the really cool thing about this system and this way of bookkeeping for the numerical problem is that for a given geometrical system, and keep in mind that I've kind of couched the problem as a sampled wire, but there's no reason why you can't modify this technique and make samples of multiple wires, like in a Yagi antenna, or have curved non-Z components of your wire. You can bend your wire around. You can make it into a helix or a circle or a coil or some crazy shape. And there are even ways to modify this so that you don't even have to necessarily have a wire. You can modify this technique to accommodate things like a ground plane, sheets of metal, and things like that. But the nice thing about this is that it puts it in, once you go and calculate all the geometrical dependencies that are trapped in this integral, you have that for the entire problem. You've calculated your Z. All you have to do is figure out, how am I going to excite this? Well, I'm going to, if it's a half-wave dipole, I'm going to take the center voltage. I'm going to put a voltage there, just like a transmission line would. And everything else I'm going to set equal to 0 volts, because I'm not going to put feeds on those other segments. And so, when you go to start playing around with four-neck, the solver that I'll put a link to that you can download, you specify which node you're going to excite, and you set everything else equal to 0. So you can set this equal to, say, 1 volt. And then, to solve for the currents, all you have to do is invert that matrix. Multiply it by excitation. And then if you get a crazy idea like, ooh, I know what I'm going to do. I'm going to make a half-wave dipole that I feed like this. I put a voltage source there and another in-phase voltage source down here. Nobody's ever thought to do that before. Let's try to see what that happens. What kind of radiating system occurs when you do that? Well, already solved this, and in many cases inverted it. All you have to do is populate that vector, multiply your inverted z by that vector, you get the new current distribution that falls out of the system. So this is a very powerful technique, but you see all of the elements of numerical electromagnetics coming into play. One, this is why there's such a difficult chicken and the egg problem in electromagnetism. All the E's and the I's, all the voltages in your system and all the currents on your wire radiating structures influence one another. They're all interrelated, which makes solving them very difficult. The interdependence causes sample problems to blow up in complexity very significantly, because you have this n squared matrix where n is the number of samples that you have. And so, Pocklington's integral equation, this technique for solving that is called the method of moments. Sometimes you'll see it abbreviated as MOM in papers and manuals and the like. The method of moments. This is how we solve it. So there are other techniques that are even a little more sophisticated for solving antennas. Finite difference time domain, finite difference frequency domain, finite element solvers, all sorts of crazy techniques. We're not going to go into any of those. We have a numerical electromagnetics class at the graduate level if you're really interested, which it is very interesting. But this is as far as we're going to get into the granddaddy of numerical techniques, because this will get you kind of whet your appetite. Now, if you want to go and use something else, like the solvers in CSD or HFSS, Pico, or whatever tool you can get your hands on, solve, you can learn those and apply them to your lab project or whatever. But for this is good enough to get us started and get our feet wet in solving radiated systems. So any questions so far? Yes?
What exactly does this?
What does this solve for? So this lets you solve for current. That's ultimately what we're trying to. You've been solving for current because intuitively, using things like that transmission line argument that I showed you in the first week of class, what I didn't tell you is that in your head, you were solving Pocklington's integral equation. It only works for really simple systems like bent wires, dipoles, and a few other things like the loop antenna, the square loop antenna. We could apply those basic principles. Really, if you want to solve an transmission line equation, you're really solving Pocklington's integral equation for 2 bars of metal. The only thing is, this is a nasty thing to actually have to solve. So instead of solving it numerically every time, there are certain scenarios like the dipole and the transmission line where you just solve it in your head. It's going to be a standing wave, and we show you the approximate solution involving boundary conditions that are open-circuited or short-circuited and make really even standing waves. And then we tell you that that's the simplest that the universe ever gets in 3025 in the first couple of weeks of antenna engineering. And then you're off on your own. You think that you can apply that to all problems. But then along comes the Yagi Buddha array. And we know that there's going to be a sinusoidal standing current on the driver, because that's a dipole. We know something like that is going to be on the director and the reflector. But how do we figure out the phase? Is it a true sinusoidal hump? It won't be exactly a sinusoidal hump. What is the phase of one of those elements with respect to the other elements? We don't know. We don't have any basis for computing. The best thing to do is solve that numerically using this system. So we're now getting into that class 3 problem of antennas that I was talking about earlier in class. Remember, class 1 is I can estimate what the current distribution is through that trick that I taught you. Now we take the blinders off, and now we can do really complicated wire antennas, because in class 3 problems, we don't know, and this is the most general class, we don't know how to estimate that current distribution. That's what we're solving for. Once we solve for this, our work technically isn't done yet, right? I still now have to take this and put this into the vector magnetic potential equation, and then calculate E's and H's and pointing vectors and integrate to get total power, use that to calculate gain, and keep on going and going and going. That's good. That's good. That's the full gamut of what an electromagnetic solver can do. But up until now, I've been lying to you, just pretending that you knew how to calculate the current in every single situation. And then when we get to aperture antennas, we get back to what I like to call the class 2 antenna problems, where we can apply some analytic formulas to figure out radiation, but we need to know what the field is in front of the antenna, kind of like a Huygens principle. To say, well, this is eventually going to turn into this far field radiation. If I know what the field is, turn it into far field estimate what the radiation is, get all the things that I need to. The old chicken and the egg problem, right? I would like to know what the current in here is on this wire, but this current depends on all the other currents and all the other fields on this wire. I can't calculate those without knowing what that current is anyway, so how do I estimate that? Well, there's a very simple, take that back, there's a very Pocklington's integral equation way of relating those quantities that is purely Maxwellian. It's a bear to solve.